Lesson 8 is going to be converting moles to particles. So we're going to be analyzing what is Avogadro's number, how to set up these ratios, and we're going to go through some practice problems. Avogadro's number is, quite simply put, a very large number, which is 6.02 times 10 to the 23rd. Avogadro's number is used to determine how many particles are in 1 mole of a given substance. The way this number was actually determined and analyzed after years and years and years of theory is that they took a perfect sphere of silicon, Si, and using a technique called X-ray diffraction, they could determine, based off the differences in distances between all of the different atoms, which they were actually analyzing in this X-ray diffraction technique, that 1 mole of silicon crystals contains approximately 6.02 times 10 to the 23rd atoms of silicon. So this number, a very big number, tells us how many pieces are in what we call 1 mole.
So 1 mole of any substance is considered 6.02 times 10 to the 23rd. So it could be any representative particle. It could be an atom, a molecule, a formula unit, an ion, anything. If we say we have 1 mole of it, that means we have 6.02 times 10 to the 23rd of it. So atomic nitrogen, which is 1 nitrogen atom, if I have 1 mole of it, I have 6.02 times 10 to the 23rd atoms, and so on and so forth with the rest of that chart.
So now let's try to determine if you have 1 mole, which is 6.02 times 10 to the 23rd particles, let's try to figure out what happens if we decrease or increase the quantity of a mole. So now let's say we take our 1 mole and we divide it by 2, and we halved it by 50%. How many particles do we have? Let's set up a ratio. If 1 over Avogadro's number is equal to 0.5 moles over x, we just have to cross multiply to figure out what our new number is, which means that we have 3.01 times 10 to the 23rd particles. Notice as 1 mole is going to half a mole, smaller, Avogadro's number is also decreasing by half. There's no magic behind this.
This is a great way to check your answers. If something is already getting smaller, then your anticipated answer should also get smaller.
But now, let's go from 1 mole to 2 moles. If we just saw that going half makes half the amount of particles, doubling it should also double it up. So when you do the cross multiplication of 1 over Avogadro's number is equal to 2 over x, you simply notice that Avogadro's number is being multiplied by 2. So therefore, you'll notice that we have a slightly bigger number. The reason why you know this is also a bigger number is we're no longer multiplying it by 10 to the 23rd. This is by 10 to the 24th, which means it has exponentially gone up a power of 10. So again, 1 mole contains 6.02 times 10 to the 23rd particles. But now let's say we have 4.515 times 10 to the 23rd particles. How many moles is that? Again, set up a ratio. 1 over Avogadro's number is equal to unknown amount of moles over 4.515 times 10 to the 23rd. So when you cross multiply and do division, you will get 0.75 moles. Noticing that the number of particles is smaller than our standard, which is the 1 mole is equal to 6.02 times 10 to the 23rd. Therefore, we also notice that our mole must be less than 1. But over here, we're noticing our exponent is also big. It's no longer 10 to the 23rd, it's now 10 to the 24th. So we set up our ratio, and again, we cross multiply and divide. You'll notice that we get 2.5 moles. All you have to do these problems are these ratios.
Using Avogadro's number, determine the quantity of particles in each sample size. So remember, those coefficients represent the amount of moles we have. So remembering that 1 mole is equal to 6.02 times 10 to the 23rd, and now that we have 2 moles of water, we can set up this ratio and do our cross multiplication. It ends up with 1.204 times 10 to the 24th molecules, which should make sense, again, thinking back to that number line. If we increase the number of moles, we should increase the number of particles. In the next example, we have 3 moles of iron 2 chloride. So 1 mole of iron 2 chloride is equal to 6.02 times 10 to the 23rd formula units of iron 2 chloride. So now we have 3. Cross multiply, you get 1.806 times 10 to the 24th formula units. In the next example, we have half a mole of CH4 or methane. So we cross multiply and we end up with 3.01 times 10 to the 23rd molecules of methane. The final example, we have 0.75 moles of NaCl, cross multiply, you end up with 4.515 times 10 to the 23rd formula units.
And again, guys, this is not a hard concept. You're just making a ratio and you're multiplying Avogadro's number by the number of moles that you have. That's it. Now in this example, we're taking the number of particles that we have and we're determining the amount of moles. This is not hard. We just did this, okay? So we do know, for the first example, we have some crazy number of molecules of ammonium ions. So why don't we start the standard? We know that 1 mole is equal to 6.02 times 10 to the 23rd. We know that. We also know that we have some unknown amount, and we don't know how many moles that is. So we put x over 3.01 times 10 to the 23rd. We will then cross multiply and divide, and x tells us that we have 0.5 moles of NH4 ions. In the next problem, we have a big amount of titanium 4 oxide compounds. But again, we know that 1 mole is equal to Avogadro's number, and we don't know how many moles the 1.505 times 10 to the 24th is, but the exponent times 10 to the 24 means it's greater than 1. So when you cross multiply and divide, x is going to be 2.5 moles. In problem C, again, we have a very large amount of atoms of neon. But if you look at the number, 4.515 is less than 6.02. So this means we're going to be having less than 1 mole. So again, 1 mole over our standard of Avogadro's number is equal to x over the amount of atoms from the problem. You cross multiply and divide, x should be 0.75 moles. And again, if you look at these on the number lines that we just said in the slides before, they should all make sense. And for the last problem, you have 9.03 times 10 to the 23rd, a number bigger than Avogadro's number. Now we have these ions of sodium. And again, the standard is 1 mole over Avogadro's number is equal to some unknown amount over 9.03 times 10 to the 23rd. You cross multiply and divide, and x should come out to be 1.5 moles.